Continuing our discussion on graph traversals, today we will see another method of graph traversal. It's called depth first search. So in this video we will see what is DFS, what are the applications of DFS, how we can perform it. We will see some sample dry run of DFS iteratively as well as recursively on a given example. And finally, towards the end of this lesson, we will implement DFS in C++, Java and Python. So let's begin. First, what is DFS? So its name says depth first search, and that's because we want to traverse depth wise. That is, we start from one node. So pick any unvisited node in this graph and go as deep as possible. That's why depth. And when you go as deep as possible, you may not find any further path. Like here, there is no further path to go from this node. So you have to backtrack. So you started from here, came here. Then here you had two options. So you cannot go simultaneously on both. You, let's say, picked this path. So you come here. Now you are stuck here. There is no other path. And there may be other possibility that there is a path to this. So you could have went there, but it's not the case. So you come back. So this is visited. You come back here and see that here there was one more path which I had not explored. So you will take this path. Now there is no path to go from here since this is directed graph and this is coming into it and not going out. So again you are at a dead end. So you backtrack. This thing is called backtracking. So when you reach a dead end or only path is to a visited node, let's say there was a path like this, still you would not go here although there is a path since you have already visited this place. So you will not visit a place twice. So again you would have backtracked, and here there are no other possibilities. So you will come back here, and here you will see that I had taken this path. There was another path which I had not taken. So you take this path. So this is also visited. Here you see that there is a path going to a node which I have already visited. So I will not go there again. So you backtrack, come back here, and you see that there is no more path here. So you stop. So from here in this graph, it was reachable from this starting node. But what if you started from some different node, let's say here. So if you start from here, you can go only in these three nodes. So if you start from here, you can visit only this and this. This is incoming edge, so you cannot go out. So from a given node, you may not visit all the nodes. You can only visit nodes which are reachable from there. So you may need to run DFS multiple times. So you keep track of one visited array whose length will be again equal to the number of nodes, same as the breadth first search case. So everything is false. 0, 1, 2, 3, 4. So let's say we started from here and let's label them 0, 1, 2, 3, 4. Let's say you start from 1. So 1 is true. Then you visit 3 and 4 from 1. So these are true. You cannot reach any other node from this. So you will look in this visited and pick the first unvisited node. So you come here, you see that 0 is unvisited. So you pick it and start again DFS, second run of DFS from here. And you see that here it's visited, so you will not take this. It will be visited. And then you will go to 2. 2 is unvisited, so you come here. And this is also visited now. Now you see that, is there any unvisited? No, so you stop. So you have visited everything. So you may need to run DFS multiple times depending on from where you start. Similarly, if it's a undirected graph, for this graph it will be every node will be visited if you start from any place. But if there are multiple connected components, even in undirected graph like this, so this is a single graph, then you will need multiple runs of DFS. So first let's look at the pseudocode for DFS. So label a starting node as visited. Then for all the neighbors of S, if it's not visited, you again start DFS from there. So this is a recursion. Now let's see a iterative approach where instead of using the recursion, we will use stack. So let's say we have a stack and it's empty. In BFS we had used queue, here we will use stack. So what we will do, let's say we start from 0. So we mark it as visited. So let's color it. So this is visited, and then you insert it into the stack. Then you see that whatever is, and on the top of the stack you see its neighbors. So its neighbors are 3 and 1. So 0, you better check the adjacency list. You will not be looking at the diagram in the code. So whatever is first in the adjacency list, you see if it's visited or not. So you see that 1 is the first neighbor. Is it visited? No. So you visit it. So mark it visited. So this highlight denotes that value in this visited array is marked as true. So 1 is visited and you also insert it into the stack. Now what is at the top of the stack? This 1. So you look at its neighbors which are unvisited. So its neighbors are 2 only. There is only one neighbor, 2. You can also see here. And it's unvisited. So you insert it into the stack and also mark it as visited. Now you see what is at the top of the stack. It's 2. So what are the neighbors of 2? There are no neighbors of 2. So you pop it out. So this popping thing would be equivalent to backtracking. Pop from stack. So we backtrack. So we pop it out from the stack. So let's get rid of 2. Now what is at the top of the stack? 1. So you look at its unvisited neighbors. There is only one neighbor, 2, but it's visited. You can see here. So there is no place to go from 1 also. So from 2 you backtrack to 1. From 1 you again backtrack to 0. So let me draw with some other color so that you don't think of it as a graph edge. So this blue denotes backtracking. So you come back to 0 and look at, so when you backtrack you pop it from the stack. Next you look at other neighbors of 0. So 1 is visited, next is 3 which is unvisited. So you push it into the stack and you also mark it as visited. Now 3 is at the top of the stack. So you look at its neighbors. Its neighbors are 2 and 4. 2 is visited. You can see here. So you look at its next neighbor which is 4. So you push 4 into the stack and mark this as visited. Now 4 is at the top of the stack. So you look at its neighbors. There are no neighbors. So you need to backtrack. So you will go back here to 3. And also that means pop 4 from the stack. Now you are at 3 and 3 is at the top of the stack. So wherever you are currently, that will be at the top of the stack. So look at the neighbors of 3. There are only 2 branches, 4 and 2. So its neighbors are 2 and 4 which are all visited. So you again backtrack to 0. And you also remove from the stack. That is equivalent to backtracking. Next, current node is 0 or the top of the stack is 0. So you look at other possibilities. There were only 2 neighbors or 2 branches, but all of them are visited now. So you remove it from the stack and now stack is empty. So you return. So what order it was printed? We visited 0, then we came to 1, then we came to 2, then we backtracked and visited 3, then we went to 4, then backtrack and we are done. So this will be the order in which it will be printed. So this is the iterative way of solving it. So what is the space complexity here? Space at max, we will insert all the nodes in the stack if it's like a linear graph. So you start from here, insert it into the stack, you insert it, and every node is inserted in the stack. Then you start popping or backtracking. So space complexity can be order of V. And what is the time complexity? You look all the possibilities, all these, and these are corresponding to edges. So if there are 5 edges, 1, 2, 3, 4, 5, you will have 5 values in the adjacency list. And then you check which nodes are connected. So a single node, multiple edges may be coming. So it's of the order of V plus E. Why V comes here? You will see that only I am looking at the edges. You see the visited thing, you keep track of visited. Even if there are no edges, you will require at least V comparisons. You check the first unvisited node, this is one. Look at its neighbor, it will not have any neighbors. Then you look for next unvisited node, you will come here, and so on. So you need to have V plus E, time complexity. So this was the iterative solution. You can implement it using stack. And this pseudocode was recursive approach. So let's see recursively. Let's start DFS from. So we saw that if we start DFS from this node, we will only visit 3, 4 and 2. So we need to start it from multiple nodes. So what we will do, we will create a visited array of size V. Everything is false. Then for I equal to 0 to V minus 1, if visited I is false, then you start DFS from that node I. And in DFS, this is, let's say, another function. This is capital DFS. So it takes one node from where to start DFS. For example, if you start from here, you will reach these nodes. And this is the main function that will make sure that all the nodes are visited. So it will trigger multiple calls of this DFS. And this DFS is taking a node S from where to start DFS. So it will mark visited S as true. Then for all adjacent node U of S, if S is not visited, that is visited, or rather U is the neighbor of S. If U is not visited, then call it again, this function itself. So if we start from 3, it will visit these and return. Then here it will check that which is the next node which is unvisited, and again start it from there, let's say 1. So it will again traverse just 1, 0 will still be unvisited. It will again continue its loop. It will not start from beginning. So this can run exactly one time. So let's say at third place it found unvisited. So it will trigger DFS from that third place and visit all the nodes which are reachable from there. And that I was still remaining, state was remaining in this call. So if I was 3 earlier, before starting this, it is still 3 when this call returns. So it will start looking from 4 onwards, which is the next unvisited node, which was not reachable from I3. So again it will start from there, and ultimately it will make sure that every node is visited. So let's run through an example. So here in this case, we start from 0. 0 is unvisited, so start DFS from 0. So this calls DFS 0. And here we mark visited 0 as true. So this is true. And for all nodes U of 0, and adjacent nodes are 3 and 1. So first it will call 1. It will start DFS on 1. So it calls DFS 1. So this is visited. And then again it looks for adjacent nodes of 1. So adjacent node of 1 is 2. So it checks whether 2 is visited or not. It's not visited. So it starts DFS from 2. So it comes here, marks 2 as visited. Then it looks for adjacent neighbors of 2. So this loop will not execute since there are no neighbors of 2. So it will return back to DFS 1. So again DFS 1 has just one neighbor. So that loop has ended for 1. So it will again return back to 0. And then here in the 0, we had called this one. So first neighbor was 1. So we came here. Next to u is 3. So it will call, this will end this thing. Let me write here again. So we called DFS 0. It called DFS 1. It called DFS 2. Then it returned and it also returned. So this is no more in this stack, and this 0 had looked at its one adjacent node 1. So it will look at its next adjacent node, that is 3. So it will call at this level DFS 3, and 3 will look at its neighbors for all adjacent nodes of 3. It's 2 and 4, but 2 is visited, so it will not execute this DFS since visited check is added here. So it will call for 4. So it will call DFS 4. Then there are no neighbors of 4, so it will return again. It will return to 3. There are no other neighbors of 3, so it will return back to 0. And there are no other neighbors of 0, so this call will end. So what order it will be printed? First 0 is visited, then 1, then 2, then 3, then 4. So let's write the code for this in C++, Java and Python. And again here the time complexity is order v plus e due to the same logic. And space complexity is order of v. Since in a given time, if it's like a perfectly linear graph, then this this recursion stack will hold all the nodes. So this stack will hold that amount of memory. And here we were explicitly using stack to, here we are simulating the stack using recursion. So let's write the code for this recursive approach. So this is the implementation of graph from our previous lecture. So make sure that you are comfortable with implementing this small graph data structure. Now we will start DFS. So what we need to do, first we will create a visited vector of bool. Initialized to false. Then we will print it, but we will print it in the recursive function DFS. And let's make it private, since we will not expose this function to our clients. This will be internal to this graph implementation. And this will also take the visited. And make sure to pass it by reference. We are printing here so that we know which order the vertices were visited. So we mark it as visited, print it, then look at its neighbors. If a neighbor is unvisited, start again this DFS. And here in the main function, we will make sure that all the nodes are visited. So we will start pick first unvisited node, start a DFS from there. This will recursively visit all the nodes that are reachable from there, and ultimately it will return. So it will iterate till the end of the vertex list and check if there is any unvisited vertex left. If there is unvisited vertex left, that means that was not reachable from the earlier node from where we triggered the DFS. So it will again start a DFS from there, and it will again recursively visit all the nodes which are reachable from there, and ultimately it will make sure that all the nodes are visited. And now we need to call this. We have added these edges. These are exactly the same graph, this graph. g.dfs. And let's see which order it's printed. It's printed 0, 1, 2, 3, 4, which is same as this order 0, 1, 2, 3, 4. Now let's write the same thing in Java. So again we will define one private function. For all the neighbors of S. If not visited U, then start DFS. And let's call DFS. And again it's 0, 1, 2, 3, 4, same order. Now finally we will write it in Python. So we have initialized the visited with false. Then for I in let's define the recursive DFS function. All the neighbors of S, if not visited U, if the neighbor is not visited, then again start DFS, recursively call this DFS from U. and that's it. And here we will check if not visited I, then can't multiply. Okay, it's the adjacency list. We need to create a list of the size of number of vertices. That did not make sense. So again the order is 0, 1, 2, 3, 4, which is as expected.